Here, we're going to use technology to graph each of the following functions. And we're going to answer a few questions about what we see, just what we notice in general, and what we can determine by each of these functions. Okay, so the first thing I'm going to notice before we even go to Desmos to graph them is that they're all quadratics, right? But they're in a different form. So I want to talk about these various forms and what they can do for us. All right, so let's graph these. Here in Desmos, I'm going to have f of x equal to negative x squared plus 10x minus 21. Okay? So I see it graphed in orange there. Next, I'm going to graph g of x equal to negative quantity x minus 3 times the quantity x minus 7. Okay, now we see the graph in purple there, and it looks pretty much the same as the orange one did, right? And in fact, they are the same graph, where they're lying right on top of each other. Okay, so now let's graph h of x equal to negative x minus 5 quantity squared plus 4. Okay, and all of a sudden I have a black graph there that looks awfully similar to the first two we graphed, right? So each time I graphed a function here, it was graphing right on top of the other ones. So each one of these functions is equivalent to the others. Okay, so I've adjusted this a little bit so I can see all the key features of this graph, right? I can see the vertex, I can see the x-intercepts, and I can see the y-intercept. Okay, now I'm going to take this graph and answer some of those questions that I had asked initially about it. Okay, so now we've graphed these three functions, and we've determined that they're all the same function, right? Graphically, we get the same thing. That's what I'm going to say when I say, what do you notice about these graphs? Let's say they are the same. Okay, meaning each one of these functions has the same exact graph. So what can we determine from the function f? So if all of these functions are the same function, they're just in a different form, what's helpful to us about these different forms? So when we look at just the function f, negative x squared plus 10x minus 21, one of the things that form gives us is the y-intercept, right? Because if we think about f of 0, we can very easily see that if we stick 0 in for all the x's there, the y-intercept is negative 21, right? Which we see on the graph. So that's what I would say about what can we immediately determine from the function f. We can see, I should say we can determine the y-intercept. Okay. What can we immediately determine from the function g? Okay, so essentially what g is the factored form of f, right? So in that factored form, if we let g of x be 0, then we know that either x minus 3 is 0 or x minus 7 is 0. And that gives rise to the x-intercepts, right, when we solve each of those. So the x-intercepts are 3 and 7. So we can easily see that in the factored form. So I would say we can determine the x-intercepts. Right? And what can we immediately determine from the function h? Okay, so the function h is what we call vertex form, okay? So we notice that the vertex of this graph is 5, 4. Do you see 5, 4 in this function here? Yes, right? So what's happening inside the x-axis there is shifting the function left or right. In this case, it's shifting it right 5 units. So the x-coordinate of the vertex is 5, and the outside constant there of 4 is shifting the graph up 4 units, so the y value of the vertex is 4. Okay, so we can immediately determine the vertex. So these forms that we just were looking at, they all have names, right? And just in talking about those different forms, those names kind of came through, right? So the standard form, the way that you've seen it in the past, f of x is equal to ax squared plus bx plus c, okay, which we call standard form. Factored form, in the form a times x minus m times x minus n, with intercepts m0 and n0, right? Going to give us easy access to the x-intercepts, right? And then vertex form, a times x minus h quantity squared plus k, with vertex hk, right? Now if we had x plus h inside there, then our h value would be negative, right? More on that in a little bit. Now I want to take a look at something with that example that we just did with the functions f, g, and h. I want to take it away from the graph. Can we algebraically show that h of x, the vertex form, is equivalent to the standard form? Can we show that that's true? And can we take the vertex form and show that it's also equal to the factored form of g of x? Okay, so let's take a look at that. So what is h of x? We're given that h of x is equal to negative x minus 5 quantity squared plus 4. Okay, so the first thing that you need to do is to FOIL that, right? So we're going to have negative x minus 5 times x minus 5 plus 4, right? Because when you have a binomial squared, you actually have to FOIL that out, right? You can't just square the individual terms in the binomial. We have negative, we FOIL that, we're going to have x squared. What's the middle term going to be? Negative 5x minus 5x, so we've got the outer and the inner there, and then plus 25 plus 4, okay? So I'm going to clean this up a little bit. Negative times the quantity x squared minus 10x plus 25 plus 4. All right, now I have to distribute the negative through the parentheses. So I'm going to have negative x squared plus 10x minus 25 plus 4. So negative x squared plus 10x, and negative 25 plus 4 is minus 21. Okay, now is that the same thing as f of x? Yes, it is. No wonder we got the same graph, right? So over here we're going to show that h of x is equal to g of x. Okay, so in a similar fashion we're going to start with h of x, and that's equivalent to negative times the quantity x minus 5 quantity squared plus 4 equal to negative x minus 5 times x minus 5 plus 4. Okay, so we have negative x squared minus 10x plus 25. We just did this with the other example, right? And negative x squared plus 10x minus 25 plus 4. Okay, so we just, we're now to the point that we got the previous example, right? We just showed once again that it's equal to f of x, but now I want to take it another step further and factor that, because g of x is in the factored form. So I want to take a negative out. That's the first thing I'm going to do. So all I'm doing is factoring out a negative in this step, right? So I have negative times x squared minus 10x plus 21. And factor the stuff that's in the parentheses there. So I want factors of 21 that add to negative 10. So I'm thinking negative 7 and negative 3, right? Negative 7 times negative 3 is positive 21. But when we add those, we get negative 10. So I'm going to say x minus 7 times x minus 3. Okay, and is that equivalent to g of x? It is, yes. Okay, all right, so I just wanted to show that if you take the vertex form, you can get it back into either of those other two forms.